hit the share, and there we go. So you should see a picture of my shining face with my glasses on so I don't look so frightening. There we go. And the lesson for today is, as promised, and I know that you've all been waiting with bated breath, and you should go look that phrase up, because it's actually, its origin and meaning is far different than any of us understand. And we will begin lesson 15. So the topic of lesson 15 is the mighty hypothesis test. So the point of hypothesis testing, as indicated by the graphic, is to try to find red umbrellas in a sea of black and find out if that's really red or if we've just hit our head kind of hard. And I will exit this HTML in a second. Much of what is discussed in this presentation is extracted from these three references. One's called Hypothesis Testing in Machine Learning Using Python by, that's a cool name, I bet I can't say it right, Yogesh Agrawal. And it's one of the blog postings on the Towards Data Science blog, something that by now we hope that you have visited at least more than once and perhaps have bookmarked it, because a lot of what you need to know and may find useful in the future at Texas Tech, there's quite likely somebody else has solved the issue just like you're trying to do, or close enough that you can copy, cite, modify, and run. Yes, actually, I think it should be cite, copy, modify, and run. I'm still working on the acronym because we just invented it ourselves collectively. Second one is called Demystifying Hypothesis Testing with Python examples by what to me is an even more unpronounceable name, so I'm not even going to try. Also at the Towards Data Science. And there's another blog post called A General Introduction to Statistical Hypothesis Testing. And so that's what today's subject is on, and it's obviously an extension of our last lesson. So let me switch over to my, oh, that's not good. There we go. Lesson 15 live. So the HTML I was looking at is this one, and we're going to work on that. It's got the preamble. And let's proceed forward. And I have no idea why the graphics fans are spinning like crazy on my GPU right now. So I must be data mining for somebody that I don't know of. Those rascally Bitcoin miners. Okay, so let's begin with what is hypothesis testing. So the hypothesis testing is referring to in this lesson, in this class, is a methodology based on some statistical inference requirements that's used in making decisions about population behavior. And those decisions are based on what we can see, our experimental data or our sample. So from a sample, we infer information about the population. And essentially what we're doing is we're going to make an assertion about a particular population parameter, and the examples today will all be on the population mean value. And then from a sample, we want to either confirm or accept that assertion. In words, the statement we're making is we have evidence in our sample that this assertion is correct, or the alternative is the evidence in the sample suggests that the assertion is incorrect. And that's all hypothesis testing really is. So when they invented these things a long time ago, they went out to the dictionary and they found as many complicated words as they could That's probably what all my lessons are like when you hear me talk, and put them in a bucket and shook it really hard, and the words were really dizzy, and then they put them into a sentence, and that's how hypothesis testing classically was created. As an example, suppose we have, on average, the students in the class are taller than 5 feet 4 inches, or a similar example is an average boy taller than an average girl in our class, or is a specific treatment effective in treating COVID-19 patients. That last one is kind of a prescient example for the day and time that we're all living in right now. All the drug companies throughout the world are scrambling to find a treatment or a vaccine that provides protection against this COVID virus. So they could give the vaccine to one person, such as the President of the United States, and miraculously 3 days later he's bouncing back doing presidential stuff. And we could base it on that one person and say, this stuff works great, it's awesome, let's give it to everyone. But that recovery on the part of him is completely explainable by luck if the sample size is 1. So instead, we use hypothesis testing to take small samples because it's inconvenient to treat the entire population and then discover the stuff's poisonous because there'll be nobody left to pay taxes. We take a sample and we can use that to infer whether or not the particular treatment is useful. So that's really all hypothesis testing is. The other two examples are probably more meaningful for us in an engineering context because those are the kind of questions we're often asking of our data. Does the data indicate that some item is bigger than some other item on average, or based on a classification, boy versus girl, is the boy item different than the girl item? And what we need is something more than just drawing pictures like we did last time. We have a method that not only helps us make the decision, it provides a good estimate of our chances of being correct or wrong. So here's how we use it. This is a cool graphic, by the way. So it's a method, it's a procedure, or a set of rules or recipe that we follow. And what it's intended to do is provide a way to evaluate two mutually exclusive statements about a population to determine which statement is best supported by the evidence, the sample data. And we're going to introduce the word significant to you in a different context than perhaps you're used to. We say that a finding is statistically significant. When we state that, that's because of a hypothesis test. And statistical significance has a fairly precise meaning that we'll get to shortly. So here's our issue. We have some question to ask. We have some universe represented by the ellipse and the red stuff in it. And we're going to go ahead and sample from this universe or this population. And we're going to use that sample to make a hypothesis or an assertion. So we might assert that the average numerical value from this population is 3. And we'll go ahead and pull a sample from that. That would be our null hypothesis. The average is 3 or less. And the alternative would be 3 or more. And so the hypotheses are mutually exclusive. That is, the H0 assertion is not supposed to contain parts of the H1 assertion, and vice versa. The H1 assertion is not supposed to contain parts of H0. And so we've alluded to that all along. So when we did our if-then stuff, we would like have if a variable is greater than or equal to some sentinel value or less than the sentinel value. And so that provides a division that's mutually exclusive. If you have them both, if you have one less than or equal, one greater than or equal, the equality would make either assertion true at some point. That's not mutually exclusive. That's actually fundamentally a mistake. So that's essentially what we're doing. Now, the important aspects in a hypothesis test are one assertion, which is called the null hypothesis, and the other assertion, which is called the alternative hypothesis. The null hypothesis, or the null assertion, is the default assumption. That might be the case where there's no difference. And in inferential statistics, the null hypothesis is a general statement, default position, or assertion that there is no relationship between two measured phenomenon, or there is no relationship or association among groups. So it's the basic assumption based on the problem knowledge. For example, a company production is 50 units per day might be the basic assumption. The alternative hypothesis, or the alternative assertion, is the mutually exclusive alternative that we would test. So a violation of the test's assumption, violation just means it fails our statistical test, is usually called the first hypothesis, the alternative hypothesis, the alternate assertion, or H1, and it's a shorthand for some other hypothesis. And it is accepted under conditions where the evidence suggests that the null hypothesis is rejected, or there's insufficient evidence for the null hypothesis to be believed to be true. And I'm trying not to completely read this verbatim because you all can read as fast as I can. The alternative hypothesis is usually taken to be that the observations are the result of some real effect. For example, a company's production is not equal to 50 units per day. And actually, these are really good examples. This is an example of what's meant by an assertion, a mutually exclusive assertion. It's either equal to something or it's not equal to something. So the single statistical test alone is incapable of suggesting specific alternatives other than true or not true. And we can finesse those a little bit and get some idea of greater than or less than, but that's about all that can be accomplished in a single test. Now, it's possible to stack to ladder a set of tests to get some guidance on what the most effective hypothesis will be. So let's look at some of the basis. The basis of hypothesis testing is an ideal of normalization and or standardization. And so all the hypotheses tend to revolve around these two terms. If you examine these two images, so the first one and the second one are conveying fairly similar pictures. The first one is simply normal distributions. 3 of them are centered at 0. That's with the mu equals 0 here. So we have our measure of central tendencies. And the different colors correspond to different variances. Notice it's sigma squared, so they're talking about variances. One of them is centered at -2, and it too has a different variance. So just to get some interactive feedback here, the blue curve has the biggest or the smallest variance. Somebody unmute themselves, and it's a very simple answer: bigger or small? Biggest or smallest?
The smallest.
That's correct. And graphically, we see that in that the range of values on the x-axis that it takes is restricted roughly to about -1.5 to 1.5. And normal distributions actually go to plus minus infinity. So there's non-zero values way out here, but they're not terribly big. The largest variance in this diagram is which one? Again, anybody unmute yourself.
Green.
Pardon?
The green.
Variance.
Oh, wait.
Largest
The red one.
variance.
Oh, no.
Well, so green, incorrect. Red, also incorrect. I already
Orange.
said blue is the smallest, so we have one color left. So that's a good example. My null hypothesis is it's the orange one. my alternative hypothesis is the three that have already been identified as wrong. So the correct one is the orange one, and we see that because its range of values on the x-axis of non-zero values is quite a bit wider than any of the other three. Now the green one is shifted to the left of the other three because its measure of central tendency, or its centering parameter, mu, which is its population mean, is -2. So one more speculation question. If this -2 were changed to a 0, what would the green curve do?
It would be centered on 0, just like the rest of them, right?
Correct. Good. All right, so let's see the narrative. In the first image, we see that there are different normal curves. I'm going to go ahead and fix something because I think that is supposed to be a bold. I wonder what happened there. That's weird. It's coming up as bold there.
If you add double underlines at the end of normal data.
Yeah, I think that will bold it for you. Yeah, there we go.
Sorry about that.
Okay, there. That's what it's supposed to look like. In the first image, you can see there's different normal curves, and we've beaten those to death. They have different means and variances. The second image is a special representation of the normal distribution. It's called a standardized normal distribution, and standardization means that we adjust things so that the mean is set to 0, and the horizontal axis is adjusted so that the variations are represented as integer multiples of standard deviation. So for example, this -1 is -1 standard deviation to the left of 0, -2 is 2 standard deviations to the left of 0, 3 is 3 standard deviations to the left of 0, and same for the positive direction. And when it's normalized in that fashion, one plus or minus 1 standard deviation explains almost 70% of the observations are expected to fall in that range. 2 standard deviations, 95%. 3 standard deviations, 99%. And anything beyond that, we get higher values. And in manufacturing engineering, they use a 6 sigma target, so they try to get everything to within 99.9% of all behavior, and then reject outside of that, and that's how you get factory seconds. And in the standard normal distribution, we actually only have to have a single quantile function and a single distribution function. And the red one, for instance, here, or the blue one, or the green one, or the orange one, are all readily converted to this standardized distribution by a simple mapping process, and that's called the z-score. And so what the z-score is a transformation that will take data that are willy-nilly distributed, if you will, and transform it onto this second picture. We use the second picture to perform our statistical tests, because instead of having to keep a track of an infinite number of possibilities, we only have to keep track of that one test. And then we transform back to the original data scale. We actually did that in our prior lessons when we log transformed data into the gamma distribution, analyzed it, and then inverse transformed back into original units. So that's a very common process, and you should never be afraid of it. It's not trivial because it's easy to make mistakes, but it's a common and important process to give us the ability to let the data talk to us and be able to see things that are otherwise hidden because of scale. So a variable is said to be normally distributed if its distribution has the shape of a normal curve. And we've actually seen that. We've actually seen the function that makes that the case. And then the graph of a normal distribution is called the normal curve, for which the mean, the median, and the mode are equal. There's other distributions where that's true, but for what it's worth, most distributions, the mean, median, and mode are not the same numerical value. And in this diagram here, these are representing incremental probabilities. So if we were to integrate this curve, which is what we did in lessons 13 and to some extent lesson 14, if we integrate the curve, we get that S-shaped cumulative distribution that we call the quantile function. That's all the quantile function is the integral of a curve like this. And by definition, or by a convention, the standard normal distribution is a normal distribution with mean 0, standard deviation 1, the second image above. So the z-score is a transformation that allows us to map real observations onto the standard normal distribution. To obtain a particular z-score, we simply take the value, we subtract off the population mean, or if we don't know it, the sample mean, and we divide that by the standard deviation. Again, the population standard deviation if we know it. If not, we can approximate it with the sample standard deviation. And once we make that transformation, now we have the ability to examine our behavior on the standard normal distribution. This next image shows another interpretation of the standard normal distribution and the some extent the definition of significance. So in the statistical significant, we're actually setting a probability value or a z-score somewhat arbitrarily. In this case, they're doing 90th percentile, 95 percentile, 99 percentile. And those are common percentiles. And we declare any differences that are in these extreme regions to either the left or right as evidence of something that's different. And then any values that fall between our arbitrarily selected significance values are explainable simply by random variation. So visualize that we have two samples, and we don't know if they came from the same population or not. So put that into your mental image, and of those two samples, we can draw pictures like this. Let's suppose one of the samples plots up like this green line, and the other one plots up like the red line. So we look at the two, red and green, the mean values, they certainly look different. And if we plot those two distributions on top of each other, they wouldn't overlay one another. There'd be another bell curve. And if that difference between the two peaks falls in these extreme regions, we might likely conclude that indeed the information is different. And that's the essence of a hypothesis test. And the hypothesis test doesn't do it graphically, we do it computationally. Depending on the questions we're asking, there's a couple types of hypothesis tests. One is called a two-sided or a two-tailed test. The other one are single-sided tests, or in this graphic here, referred to as a right-sided hypothesis. In the two-tailed test, we're posing questions of the nature that, is there a difference between group A and group B in a certain comparison? And that's all the question is there a difference? The directional or the one-tailed test is a little bit more precise in that, is there a difference, and is the difference this particular value? And that's the main fundamental difference between one and two-sided hypothesis testing. And again, we will arbitrarily, well, actually not arbitrarily, we will a priori, ahead of time, choose the level of significance that we think is important. So if we think it's important that there's really strong evidence of a difference, which is what we would do in medical research, that level of significance, that alpha value could be somewhat small. If all we want is a suggestion of difference, we could accept a higher alpha value, and in doing that, we will entertain the probability of a higher level of mistakes. The smaller the alpha value, if the test indeed rejects, economically usually costs quite a bit more dollars to get enough data to make that. We'll talk about that more later. I think I'm rambling now. So let's look at significance. So significance in the data science sense refers to that level of probability at where we declare things are the same and things are different. So when someone states that there's a significant difference, in general colloquial talking, if we're just having a conversation, and I say, well, there's a significant difference between the speed of the black car and the blue car, and the black car being let's see, something I can't own, a Lamborghini, the blue car being my 1997 Corolla. They go different speeds. All I'm saying is that the speeds are different. But if I were to qualify that, there's a statistically significant difference in speed, and the Lamborghini tends to go 100 miles per hour faster than I can ever achieve with a Toyota. That's a more precise statement because I'm actually stating or implying that I've selected a probability value to support that difference. And to complete the colloquial statement, I should go as far as to state what that probability value is. The Lamborghini is at least 100 miles per hour faster than the fastest I can make the Toyota go. I have 95% confidence that assertion is correct. And that would be a full statement of significance. So bear that in mind in your future writing. What we tend to use in my research to avoid being critiqued for using the word significant, we use substantial, because that's a value judgment and not a p-value. I mean, just a arbitrary value judgment, and that allows us to express that we see differences in these two data series, but we have not bothered to do any kind of hypothesis testing to find out if that difference is meaningful or not. And we usually state it that way because the next sentence is, but if you pay us a few $100,000, we'll be happy to do the research for you. So the p-value is an important term that we'll see repeatedly, and it has a couple of interpretations. The p-value, or the calculated probability, is the probability of observing the collected data given that the null hypothesis was true. And the p-value reflects the strength of evidence against the null hypothesis. So we will encounter two situations in hypothesis testing. One is that the strength of evidence is big enough, and the other one is that the strength of evidence is not big enough. So the p-value is compared to a pre-selected alpha value or significance value, and if the computed probability is big enough or small enough, then we can use that as a way to help us make our reject or accept decision. I guess accept is not the correct terminology. Fail to reject or reject. Keep in mind that we usually have two parts of the sample that we're comparing, and so you can visualize that there is a second curve here, and really all the p-value is doing is measuring the shared probability, the portion of the curve that they overlay one another. As the curves move farther and farther apart, there's less and less shared portion. And did the screen just black out? Because mine did.
We can see yours just fine.
I'm glad you can. Now I'm going to have to try to figure out how to move the mouse with a screen I can't see. Okay, I got the little screen working, so I'll look at that one. You need so visualize that there's a second bell curve right here, and they're not overlaying each other, but they're shifted quite far apart. When we get to the examples, I'll see if I can construct in a hurry a visual example to illustrate that. So for instance, if we're performing a test where the data sample was normal and we calculate a p-value of 0.7, we would state something like, the test concluded that the sample was normal. We failed to reject the null hypothesis at a 5% significance level. The computed p-value was 7%. And the significance level can be inverted by subtracting it from the value 1, and then that produces a terminology called a confidence level. So the difference between significance level and confidence level, they are the ones complement of each other. So a statement such as, we found the test data was normal, we failed to reject the null hypothesis with 95% confidence interval. So here's a cool example, just in words. Suppose you have a coin, and you're playing the common back alley game that everyone called You Bet Your Life. And the person flipping the coin says if the coin comes up heads, you get to continue living. If the coin comes up tails, you're a goner. And if you watch the movie No Country for Old Men, the guy in the country store lucked out. And anyway, it's a creepy movie. So let's suppose you don't want to play the game yet. You say, well, I want to see if this coin is fair. And so your null hypothesis is, it looks just like a coin. So you assume that yeah, it's probably fair. That'd be my null hypothesis. But if it's a weighted coin, I want to test that with a rejection value of 5%. Or if I can obtain enough evidence in a few tests such that I conclude that the fairness of the coin, the chances of the coin being fair is less than 5%, then I know it's a tricky coin and I can walk away and keep my life and let the You Bet Your Life guy pick on somebody else, which morally is not a good decision, but as far as your life is concerned, it's brilliant. So our alternative hypothesis is that the coin is a trick coin. So let's toss the coin and we calculate the p-value as we proceed. So if we toss it one time and the result is a tail, we have a p-value of 50%. So there's 50% chance that there would be a head or tail when we have a single sample and it came up tail, which is one of the two possibilities. We toss the coin a second time and it comes up tails again. So now the p-value is reduced to 25% because we have 50% over 2 trials. And if we toss it 6 times in a row and we get tails every time, at that point our p-value is 1.5%. But we set our projection value at 5% error rate, and so we're beyond that. We have a much different error rate than we would expect for a fair coin, and so we would conclude that this coin is not fair and we reject it. Now we're gonna show functions that perform the work for us. To read more about p-values, you can look at these 3 references. Towards Data Science, What P-Value Tells You, www.dummies.com. I usually avoid stuff that says for dummies, although often actually it can be quite useful. And Key to Statistical Interpretation, also another web link. So these are all good choices, and there's quite a few videos here. For those of you that are going on in engineering and are one actuarial science person, especially actual science person, you need to look at these because this p-value is not going to go away as soon as I scroll down on the page. You're going to have to come up with a mental model that works for you to understand. I have one that works for me, but I think terminologically I'm wrong, so I won't share it with you all. So let's look at this idea, reject or failure to reject. The p-value is a probabilistic result. And so it means that we've interpreted the result of a test, and we actually don't know whether it's true or false, only that we have evidence that supports one or the other outcomes of the assertion. So rejecting the statement, rejecting the null hypothesis, means we've identified sufficient evidence from a sample that the null hypothesis is not likely. If that's not the case, that means there is not sufficient evidence from the example to reject the null hypothesis. So we often think about the test in terms of the dichotomy of rejecting or accepting. The danger is that if we use the word accept, the language suggests that the null hypothesis is true, and we never know that. We don't know it's true. All we know is that we have evidence to suggest that the null hypothesis is supported, or we have evidence that implies that the null hypothesis is not supported. And that's probably the level of commitment that we should make in the writing part of our interpretation. So stuff that comes out of statistical tests, there's a lot of hedging language that you'll see wrapped around it. And normally in other contexts we'd say that that's a cop-out, but in hypothesis testing, hedging language makes complete sense and is justifiable. So let's look at the kinds of mistakes that we can make. Because the result of a test is itself a probabilistic outcome, that means that the test may suggest a particular outcome and in fact be incorrect. So if you've heard the terminology false negatives and false positives, that's quite common, especially in medical research. And so again, my screen going back, again the President of the United States apparent success with monoclonal antibodies in 3 days from sick to well, that could be an actual outcome, and that's awesome. Or it could be a false positive. Something else made him get well. One possible explanation, he actually wasn't sick in the first place, but I don't really want to go there. I'm not trying to critique him per se. I'm just using that as an example. So that behavior could be false positive. It could indeed be correct, and we've discovered a cure for our disease. Or other things could have led to the rapid recovery that had absolutely nothing to do with the treatment. So when we conclude that the evidence supports the the null hypothesis, and in fact that's not true, that's called a false positive. If we falsely rejected the null hypothesis. Alternatively, if the null hypothesis is true and we concluded it's false, that would be a false negative. And in your other statistics classes, they'll talk about type 1 and type 2 error, and that's really what these are talking about. But I think it makes more sense to just look at the contingency table of the 4 possible outcomes or decisions that we, the analysts, make. We could conclude that the null hypothesis is true when in fact it's true, and that's happiness. So we got the happy face here, and that has a probability of occurrence of 1 minus alpha. Hence, that's what we talk about 95% confidence. But it also has a probability of failing where the null hypothesis is concluded to be true when in fact it's not, and that has a probability of beta. It's called the power of the test. And it goes by the name of a type 2 error. So we conclude it was positive. It's not. This is the false positive result. Alternatively, our sample can indicate that the null hypothesis is rejected when in fact it shouldn't be, and the probability of that occurring is alpha. So the tests we're describing are designed to actually have pretty good control on false negative decisions, and we get sad face here because we've made a mistake, and it won't crop up until after we've made a huge decision, and then it will rear its ugly head and will look like fools. And nobody wants to look like a fool if you don't have to, unless you're a stand-up comedian, in which case you make millions of dollars a year looking like a fool. The other outcome would be we conclude that the null hypothesis is to be rejected, or the alternative hypothesis is not rejected, and we're correct, and that has a probability of occurrence of 1 minus beta, and we get happy face. So 2 of our outcomes are happy face, 2 are sad face. And we have some control over the probability of a sad face in the case of type 1 error, and depending on the type of test, we can control beta, which is called the power of the test. And you'll learn more about those in a proper statistics class, especially the power of the testing, because that's actually a fairly tricky thing to do. So the 2 types of errors are type 1, where we incorrectly reject null hypothesis, and type 2, where we incorrectly fail to reject null hypothesis. And a far better explanation of type 1 and type 2 error is this particular picture. So here we see a person who's not a doctor, but he plays a doctor on TV, and a woman who appears to be quite pregnant and actually really close to having her child. And this one is an older gentleman, gray hair, sleeveless sweater, and these are the kinds of outcomes. So the pregnant woman is indeed pregnant, and the doctor does his hypothesis test, pulls out his Jupyter notebook running on his iPad, and concludes, "Ma'am, you're pregnant." So indeed she was pregnant, and the test indicated that she was pregnant. That would be a case of a true positive, and that's right up here, happy face. Secondly, the doctor didn't even use his iPad. He looked at the man and said, "Yeah, men can't be pregnant, so you're not pregnant, sir." Also a true instance. A type 1 error would be running the program, looking at the gentleman and saying you're pregnant, because in our planet, males don't usually become pregnant. So that would be a type 1 error, a false positive. His test has concluded that this gentleman is pregnant when in fact he's not. And then the type 2 error would be runs the test and reports to the pregnant woman that you're not pregnant, and when in fact she's quite pregnant. So all statistical tests have some risk or some probability of making either of these types of errors. They're impossible to avoid. So false findings are more than just possible. They are probable. They're likely to happen. So what we want to do is control the likelihood of those errors. And there's main way to control it is by choosing the significance level, keeping it pretty small so that the type 1, make sure I get this, so that the type 1 errors are well controlled. And then the second way is to choose a testing scheme that has high power or very low beta to prevent type 2 errors from happening. So some more discussion on the type 1 and type 2 errors. You can learn about it at Wikipedia to actually learn what is meant by type 1 and type 2. Here's a nice blog post at statisticssolutions.com that describes the difference between type 1 and type 2 errors. And never been to this blog. That's kind of cool. And another blog post on type 1 and type 2 errors. I'm intentionally taking that one just to see what it looks like. So yeah, that's a fairly classic picture. Oh, excellent! I don't have to make up my own picture. I do have to not have to pay for it. So here's what our hypothesis testing are doing. So we have a sample, and it's testing if the null hypothesis and the alternative hypothesis, how closely the two probability distributions overlay one another, given we don't actually know what they are. Oh, this thing really wants my money. And so the alpha value is the shared probability. It's this portion where the two distributions overlap. So the closer that the samples indicate that alternative and null hypothesis are to each other, the more shared probability there is, and the p-value, the computed p-value, goes up. And the further apart they are, the p-value, the shared probability area, goes down. So that's a pretty cool blog post. So let's review some important statistical tests. There's tests that are based on different different distributions. So what we're trying to test in the first category is what the distribution type is. The second category are tests to compare sample means. The third category is a type of test called a non-parametric test. So the parametric tests, by definition, depend on some underlying distribution. It doesn't have to know what the parameters of the distribution are, but it does have to know that it's from a distribution. And the non-parametric tests make no such assertions. So the non-parametric tests can be used on pretty much any kind of data. Naturally, the trade-off would be is they have quite a bit less power. So the value of beta, that type 2 error, goes up on non-parametric tests. And there's more than just these 11 that are listed here. So ones that we will examine over the course of the next few hours and days are a t-test, paired t-test, ANOVA, and repeated ANOVA we'll get later on when we get into the regression part of the class. And we'll look at Mann, Whitney, and Wilcox sign. I think I have an example called Bartlett's test, which is a variation of these. Some other ones, Kruskal-Wallis, Friedman, and so forth. And they're different, but they all work about the same way. Is you supply your observations to the test, and it makes comparisons. So now we get to the scripting part of the lesson. So here's a test for determining whether the data in a sample appears to be Gaussian distributed. So Gaussian distribution and normal distribution are essentially the same creature. The default hypothesis is that indeed the data are Gaussian distributed. The alternative is that they're not Gaussian distributed. And what the test is asserting is there sufficient evidence in the sample to support Gaussian behavior. And so the test itself is quite simple, because we just load in the script, and we apply the data to the test, and what it's going to do is it produces a computed p-value. And then we, the analysts, decide what that p-value should be, and if the computed value is bigger than a particular value, we conclude it's Gaussian, and if it's smaller, probably not Gaussian. So let me run this script, and it doesn't run because I don't have something loaded in. Oh, I don't have a kernel. Kernel, please. Ooh, that's undesirable behavior. There we go. Okay, so this says the value of the computed test statistic. And if we went and looked at the code for this Shapiro test, it'd probably be a page of Python that interprets our list and makes some necessary calculations. And the computed p-value is 0.19, and our level of significance that we selected was 0.05. Let's just go ahead and change that. You probably should never use a p-value of 0.5 because it's just plain misuse of it. But if we change that, you'll notice that the outcome is quite a bit different. And then if we're from the San Fernando Valley, we want to be for sure, so we go really low. And at that a really small p-value, we would conclude that it's Gaussian. And we return it to the actual example. A second test is called D'Agostino's K-squared test, and its goal in life is to do the same thing, but in this case it's working on third and fourth moments internally in the test. It's called the normal test in the SciPy stats package, and again we will use the package. It returns a p-value and it returns a test statistic, and we will test it at a 5% significance level. Run it. Ta-da! And this one gives us a nice, interesting warning. So let's go ahead and interpret this warning, because you guys are likely to get the pink screen of death and potentially go, oh my God, I did what you did and it didn't work. When in fact, all it's telling us is that the kurtosis test that we're using, it's only supposed to be used for sample sizes bigger than 20. And we gave it a sample size of 9 things. So it issues a warning, and it goes ahead and performs the calculations anyway. And that's a standard exception tracking, is issuing a warning, because we as analysts can interpret that warning and go, oh, I did something that I didn't expect to do, or I can say, well, I only put in 9 values, so it makes sense to me that it's issuing a warning. To learn more about normality tests, you can look at the Gentle Introduction by Jason Brownlee at machinelearningmastery.com. So this is another blog entry, and that'll be a good one. And now we're getting to some parametrical statistical hypothesis tests. You will get more of these in your proper statistics class. In fact, I'm going to beat this to death to you. And what they'll do in your statistics class is you'll learn how to calculate the test statistic. In this case, the computer is going to do it for us. And then you will use that test statistic, and you will look up in a table of t-test values the equivalent probability value. In this case, the program does it for us. And then you will interpret that result and make a decision on whether they're the same or the difference. So here we have 2 lists. One's called data 1, one's called data 2. And what we're going to be comparing is whether the mean values in those 2 lists are the same or different. Now we have no expectation of those 2 lists, even if they are the same, if we get the mean values, getting them identically the same, because they're a sample. So really we're testing, are they close enough to one another to be declared the same, or are they too far apart? There are some underlying assumptions on the t-test. The first is that each sample is independent and identically distributed, and that's a fairly precise definition in statistics that you learn more in your class. In cases where that's not true would be one of the sample values affects subsequent sample values. That's not independent. And if the data 1 and data 2 are from entirely different distributions, then that's not identically distributed. So that's a fairly precise requirement, often met in practice. So that's a good thing. And the other stipulation is that the observations themselves are normally distributed. If we make few enough of them, we can usually keep that true. And then the other one is that the observations in each sample have the same variance. And the variance is usually referring to the population variance. So actually, I'm going to suppress some of the output, right? Actually, I'm going to break this apart because I actually want to look at the two lists. Okay, so I've loaded in the two lists. Now, who can tell me how to learn what the mean value of data 1 is? Okay, I'll do the hard work. I'll type in data 1. Preferably do it correctly. Is there a method that's associated with lists that gives us the ability to get the mean value?
Isn't it just data1 underscore mean?
I think it's dot mean, but we'll find out in a second. And if I'm wrong, it'll give me pink screen of wrongness. So you said underscore. Let's see if that's... Okay, so data 1 does not have a mean value. How do we go ahead and take advantage of that? We can use, I think it's NumPy. So we'll import NumPy. So how do we turn data 1 and data 2 into NumPy objects? Y'all got to help me here because I'm doing this from memory. Array, right? I think it's array. And you 80 people are the most useless helpers on the planet. You're worse than my cats.
They're actually typing in the chat box. So.
Oh, because they can't talk? What, their mouths are broken?
I think so, probably.
Okay, well...
Their jaws have dropped after learning about hypothesis testing.
No, they'll learn more from the actual laboratory. Okay, so it looks like we've created two objects. It hasn't protested. Now let's go ahead and use the syntax. It's mean. Cool, so object 1 has a mean of minus 0.32, and let's look at object 2. Minus 0.15. So are the data the same or different? Use your voices. Well, so the computed mean value for those two strings is indeed different. And I forgot if NumPy has a standard deviation. Let's see. Does not. And the other one would be STD. Very bad method naming choice. Okay, so the standard deviation of object 2 is 0.79. Standard deviation of object 1 is 1.38. So our two simple things are different. Are they the same or different? Silence still. I forgot if describe is a NumPy feature. We'll find out in a second.
Liana, you used to be very active in helping us. Come on, unmute.
So NumPy has no attribute called describe. That must be Panda's deal, right? Yeah, so the whole point of learning this, folks, was to be able to do this stuff. Good thing I caught that spelling error because you all weren't going to help. So now in pandas, what I want to do to those, I want to turn those into data frames. I wonder if pandas can do a data frame. It's called pandas.
You spelled pandas wrong.
Yeah. There, finally. When I make a mistake, you all can be helpful. Thanks. I'm not sure this syntax is correct. Well, okay. Did obj1.describe. Okay, good. We have a descriptor. Let's go ahead and wrap this in a print function. Why am I wrapping it in a print function? I'm asking out loud. No one will answer. You can at least say, I have no idea why you're doing that. I'm doing that so I can compare the two immediately. Okay, so there's our two lists expressed using tools we already know. So each of them has 10 things in it, so that's nice, that's comparable. The mean of list number 1 is minus 0.32, the mean of list number 2 is 0.15. Standard deviation of the first list is 1.4, standard deviation of the second list is 0.83. The smallest value on the first list is minus 1.8, smallest on the second is minus 1. The median of the first one is minus 0.5, the median of the second one is minus 0.3. The max value on the first is 2.8, the max value on the second is 1.18. So again, I ask the question, are these data from the same process or not?
No.
Okay.
Oh.
So we have a claim of no, and let's go ahead and run the student t-test, and we get the result that they actually are from the same process at a level of significance of 5%. So what we human beings see as difference, there's still sufficient randomness to explain these two data streams as being the same data, and not the same data, from the same underlying distribution. What we've actually just tested, we've tested that the means of the samples are equal to one another. And that is the power of a statistics test. Let's see if we can get them to be a lot. I can't do that in a hurry. But if we jack with data 2 or data 1 enough, we can pull them far enough apart. If we return to, see which was the blog I wanted to do. That one. So what we just did is we compared two data series, data 1 and data 2, and yes, we have to go ahead and spend money. And we looked at the five number descriptors, and the 5 number descriptors gave us a picture like this on the screen. They were apart, but the shared probability wasn't small enough for us to conclude that they are significantly different in a statistics sense. There was enough shared overlap that they were considered to be the same distribution. Let me show one other thing and we will proceed forward unless I just broke it. So I'm going to intentionally create a second data stream that actually is identical to the first one. And let's see what the computed p-value is when we do that. So this is how I keep track of what p-values are trying to tell me. Because I often forget, is the p-value supposed to be small or big, accept, reject, especially when we get to some more exotic tests. So data 1 and data 2 are now identical. And let me do that down here. And so first we'll do our number described. So those are now identical, and and obviously those are from the same distribution. The computed p-value, I think, is going to be 0.5, or actually 1. So it's a two-tailed test. That's kind of cool. It's already built in. So we do that, and the p-value is 1. The test statistic is 0. Probably the same distribution. Yeah, damn Skippy, it's probably the same distribution. Those are identical samples. So what this tells me is when the p-value is big, we'll conclude that it's the same distribution. When the p-value is small, we'll conclude it's different. And the level at which we're making that cut is, in this case, 5%. So this actually introduces another important learning point. The reason we're actually printing out the statistic and the p-value is a built-in quality assurance thing. So with real data, if they're real samples, that blue highlighted line should never happen. If we get that, we've probably made a mistake like I have done in here intentionally, and we have compared a sample with itself. And,
Professor, I have a question.
Yeah?
So what did you set up the p-value to be more than 0.05? Or is it just a random number?
No, it's not random. It's a predetermined level of significance at which you are going to decide that things are different or the same.
Okay, so then, so that the p is equal to 1.00, does that mean that it's 100% identical?
In this particular instance, it does, but don't interpret it that way. This simply says that the shared probability of the two distributions is 100%. And if we return back to that picture that I keep being unable to find, so look at those two distributions. If the distributions are I am really tired of that trying to sell me an e-book. If the distributions are the same thing, they're right on top of each other. So the shared probability is completely 100%. So this is a good example. So when you get p-values of 1, the other one would be if it's a using a one-tailed testing methodology, you'll get a p-value of 0.5. That usually means you've made an analyst's mistake. You've unintentionally compared the same data with itself. There was
okay, and then is that stat value, is that a level of difference between two data sets?
The stat is a test statistic.
Test statistic.
So a test statistic might be a formula that looks something like this. This is not. This is a z-score, but test statistics are simply formulas that produce a result. And that test statistic is then compared to an underlying probability distribution to determine the shared p-value. So let's go ahead and look at what the student t test statistic is. And that should be down here in a reference. Oh, crap. Hypothesis test. Let's see what we have in this blog. You probably will have an example of what the test statistic is. Oh, please do. So notice here in the procedure, calculate the test statistic. And t-test is what we're talking about. Let's see if he actually has. Dang it. So there is the test statistics right there. So it's taking the mean of the first sample, and it's subtracting the mean of the second sample. It's dividing by an estimated or a pooled variance of the two samples, and that is the test statistic t. And that particular t-value is distributed according to a probability distribution called the student t distribution. And so what the test statistic is t. We can actually do that all by ourselves, no help. Right here, let's go ahead and make our own test statistic. See, object 1. I think that will work, and then we will print my test statistic. And let's go back to the original data structure so that it's interesting, and we'll do it here. I just realized there would have been a smarter way to do that, but I'll leave that be. Okay, so now I'm returning to the original example. So we do that, and the test statistic is minus 0.3. And if we do that, the test statistic is minus 0.17. So I have something, oh, actually I don't have the complete test statistic, my bad. I need to divide by the pooled variance. So sigma over square root of n1. So now I need to put this in the divisor. So we'll try to figure out how to do that. So the divide part's easy. Okay, so how do we get the standard deviation of the first object?
Electrically linear parentheses are well. You have one extra closed parentheses.
No, it's stupid. Editor's a piece of crap. Okay, now how do I get the first? Thank you. How do I get the first standard deviation? We get our STD from that one. How do we get the second one?
Object 2 dot standard
Got it.
deviation.
Good. STD. And then we need to divide by the count of n1. So what is the method to obtain the count of objects? I bet you it's the word count, actually. That seems kind of obvious to me. So let's give that a try. obj1 dot count. And that has to be raised to the 1/2 power. And then we do the same thing here. So can you kind of see why we want to use built-in packages if we can find them? All right, so now you have to help me group terms to get the thing working correctly. I think that term is to be grouped, and that term is to be grouped, and then the whole thing goes into a group.
What's the shortcut you're doing to do that? To put parentheses on the left and right side immediately.
I'm just highlighting where I want that to happen and typing parentheses, because the integrated development environment does that automatically. You might think that's cool, but to me, because I'm older than dirt, I find that really annoying. So if I've not made a
So that's the reason, because I also find that annoying, but I didn't know that it has something to do with my age. Okay.
Yeah. So what we've done here is I think we've implemented the formula for the test statistic. And so now we should get a minus 0.326, or we're going to get the pink screen of we screwed up. I still have something wrong. Maybe it was n-1. Let me go check the test statistic. Hopefully you're getting the idea. Now it says n1, n2. Size of sample 1, size of sample 2. The variances. Interesting. So I'm pretty sure I have the script. Object count to the 1/2 power. Group that. We added object 2, object count to the 1/2 power. Well, I have something wrong in my test statistic calculation, but I think you get the idea. So this test statistic is something like that. I'm going to go ahead and suppress it. Actually, let me try something real quick. I should get a test statistic of 0 now. Okay, so I've got part of it correct. I've got something incorrect in the denominator, and I can't find that in the next minute, so I'm not even going to try. But that's all these test statistics are, is the package is evaluating a test statistic, and then it's using the value of this test statistic to compute a p-value based on some underlying distribution. So the student's t-distribution, it's actually a type of normal distribution that's been jacked with a little bit. So
I think you had standard deviation, but I think it was variance they were showing, right? Wasn't it sigma?
So sigma is standard deviation.
Oh.
Sigma squared is the variance. But you're right. I might be. Yeah, they're showing standard deviation.
Oh, okay.
So I got something minor wrong in there, and let's save that for another time. So a second type of t-test, let's continue because I actually want to get to a real example that's at the bottom of this, and I'm burning through time. I've got 6 minutes to go. Actually, I'm already 4 minutes over. Are paired tests. And so in pairing, it means that each sample is paired. By pairing, it means that this 0.873 is somehow directly associated with that 1.142 and so on. So pairing is ultimately it means that the sample counts are the same. So we already know there's 10 things in these two data sets, and if they're pairing, the interpretation of the test statistic is slightly different. We'll run it, and we've already concluded ourselves that these are probably the same distribution. Another test is called analysis of variance, and what analysis of variance does is it computes the variance in each of the samples, and then it determines how explainable that variance is in terms of an underlying normal distribution. We'll learn more about this when we get to regression. To implement an analysis of variance test is pretty straightforward. First, we load in the test, and so this is from SciPy Stats. We would read what the syntax of the test is. In this case, they're comparing data 1 with data 2, data 2 with data 3, and then data 1 with data 3. So there's a series of procedures that are involved, and it's going to compute a p-value for the assertion that data 1 and data 2 are the same, data 2 and data 3 are the same. Well, it just broke data 2. And then data 1 and data 3 are the same. And running that's trivial. I'm just clicking it, and we conclude that at the 5% level, we're the same distribution. So non-parametric tests, personal favorite, are the only requirement is that the samples are independent, identically distributed. In many cases, that's fairly straightforward to establish is true, and that we can rank each sample. And so what a non-parametric test does is it takes two samples, much like our Weibull plotting position, ranks them, and computationally does the same thing we did when we plotted the blue and the gold curve. It sees how close or how far apart they are. And then it will compute a test statistic, and from that statistic it has an underlying distribution of what that statistic should be and can interpret a accumulated probability value for it. So here we have the same data 1 and data 2 again, and what the procedure is going to do is it's going to rank them from small to big, rank them from small to big, then it's going to compute a test statistic, which we'd have to go look up what it is, but it keeps count of the positive and negative differences, and then an associated p-value, and it's called the Mann-Whitney test. And we run it, and it tells us that the accumulated p-value or the shared probability is 23%, and we've selected that if the shared probability is bigger than 5%, we can conclude they're the same, and if it's smaller than 5%, we'll conclude they're different. So the evidence here is that these are from the same underlying process. Another one is Wilcoxon signed rank test, very similar operationally. and it's quite similar to Mann Whitney, and in this case it ranks stuff, computes differences, subtracts from the differences we'll get positive and negative numbers, and then it ranks the collection of positive and negative values and performs a statistical test on that. Same conclusion here, we'll get probably the same distribution. And then there's Kruskal-Wallis. Actually, I don't know how this one works internally, but again, we're doing the same kind of non-parametric test. You'll notice in the assumption at no point did we make any assertion of what the underlying distributions are. So these are really useful when you have data that's flopping from all over the place. And we run that, and ta-da, we get the same distribution. So now that I've got you thoroughly confused, let's go ahead and do this on some real data. So here's an example of some real data from a construction site, somewhere in the Houston area. And the background, the reason we would do this is in this particular case, Clean Water Act requires that stormwater discharge from construction sites that disturb, at the time, 5 or more acres. The law has been changed now to 1 acre. Can't convey pollutants off-site. And to prevent that, we implement things called stormwater pollution prevention plans, and you've seen those. Those are like storm fences and stuff that are on construction sites. And specifically, the permit says that we have to provide for 80% solids removal, and that total suspended solids can be used as an indicator parameter rather than as an indicator parameter. So what we want to test is there a difference in stormwater, total solids, and total suspended solids prior to construction activity on a job site and during construction activity on a job site? And I will go ahead and, spoiler alert, yes there is, but let's go ahead and convince ourselves on that by letting the data talk to us. And so what we have is our two files. One is called pre-construction, and so we have dates, and we have total solids and total suspended solids, and we actually have rainfall associated with those particular dates. And then we have during construction, and so naturally we collect way more data during construction. We've lost the date column, but we still have total solids, total suspended solids, and rainfall. So those are our two data streams. So these data, even though they have dates, they're not time series. So we can safely assume that each generating rainfall event was independent, therefore independent samples. And our task is to analyze these and decide if construction activities impact stormwater quality in terms of solid measures. That's a fairly straightforward thing to do. So let's go ahead and import some of the tools that we're going to need. So we do that, and then we'll import the two files that we just looked at. And let's look at the pre-construction file and the during construction file. And we see the main difference between the two, other than count. So 36 items there versus 16. So our sample sizes are now different. And we've lost the date in the during construction column. But we have the important ones. We have total solids in both cases and total suspended solids in both cases. And whether we use it or not, we have rainfall in both cases. So let's go ahead and describe our pre-construction data. So we use our friend, the describe method. We do that, and we learn that in pre-construction data, the total count of observations is 17, a total solids of 462 probably parts per million, total suspended solids of 286 parts per million, average rainfall in the 17 events of just less than an inch, maximum rainfall 3 inches, maximum total solids 1,700 parts per million. If we do the same for during construction, we see different values. So during construction, the mean value of total solids is almost 10 times bigger than pre-construction. So right there, we might be tempted to stop. The total suspended solids during construction is also almost 10 times bigger. The rainfall is, the mean value is roughly the same, but the maximum is nearly twice what we observed in the prior case. So let's make a box plot of the two. And we do that, we look at our pre-construction box plot for the total solids, total suspended solids rainfall. And we'll do the same for during construction. And now we ask ourselves, are the box plots different? That'd be a yes or no question. Somebody chime in. What's different between the two?
Scale.
Good. Good observation. That's correct. So the scale here is quite a bit different than the scale here. Also, we have more of these isolated markers or outliers, if you will, relative to the main portion of the distribution. Does it look like there's any asymmetry in the distributions?
What was the question?
Is there any evidence of asymmetric behavior? So asymmetry means that they're not bell-shaped, that they're smushed to one side or the other.
In the bottom one, the TSS during or construction seems to be to one side.
Yeah, good observation. Same thing with the total solids, actually. In the pre-construction, there is asymmetry, but not nearly as evident as in the during construction. So let's look at the rainfall pre-construction. The median rainfall is 0.7, and if we look at the rainfall during construction, the median value is 0.55. So the median rainfall is actually less during the construction period, which is kind of how you're supposed to do it. You want to do bare earth construction during periods of low rainfall, and we still have some high rainfall events, but generally speaking, one might conclude that the rainfall looks about the same. So let's look at box plots, pre and during. Not exactly the same, but let's ask the question, because this is important for our water quality decision. If the rainfall variability is enough, then we can't safely conclude that the differences we see in solids has anything to do with construction. It could just as well have to do with different rainfall. So we want to ask the question, are the mean values the same or different? And so we'll use the Mann-Whitney test. And we do that, and we conclude that it's probably the same distribution at 5% rejection level. And so how we interpret that is we have no evidence in these samples that the mean rainfall behavior varied between the two study periods, pre-construction and during. If we don't trust the Mann-Whitney, we can try a t-test. We can't use paired t-testing, but we can use an ordinary t-test, and we'll pretty much arrive at the same conclusion. We do not have evidence in the sample that the rainfall was significantly different in a statistical sense at the 5% rejection level, or 95% confidence that the rainfalls are, for all practical purposes, the same in a statistical sense. So from these two tests, we conclude that the rainfall data came from the same distribution. So the question, do the two construction phases represent approximately the rangeful conditions, can be safely answered in the affirmative. So we conclude yes, the range is essentially the same. So now let's continue and ask the same question about total solids. So we proceed the same way. So keep in mind the cite, copy, modify, run acronym that we use. That's all that's going on here. So we look at for pre-construction and during construction, the pictures look quite different. The scales are quite a bit different. And during construction phase, we're seeing about 5 to 10 times greater solids. But let's go ahead and apply some tests to support or refute that assertion. So first we'll do a non-parametric, and what we're going to test is the mean value during construction different from the mean value pre-construction? And we will again use 5% as our rejection level. So when we run the test, we have a p-value of, screen went black again, p-value of 4.2%, which is smaller than 5%, and so we would conclude that these are probably from different underlying processes. I mean, I know we kind of saw that anyway, but now we have firm statistical documentation of that. If we did the same thing with t-tests, I believe we get the same result. And we have probably different distributions. So we have, if p is bigger than 0.5, so both tests indicate that the data derived from distributions with different measures of central tendency. And so we could conclude that there is no evidence in the samples that the two phases are the same with regards to solids. So let's now ask the question about normality. So there's a test called normal test, and it tests the function that a sample comes from a normal distribution, and it's based on D'Agostino and Pearson's test, combining skew and kurtosis. And we're going to get a warning because our sample size is pretty small. So now we're asking the question, does the pre-construction data for total solids appear to be normally distributed? And go ahead and run the test, and we would conclude that it does not appear to be normally distributed, and we can probably see that to some extent from the actually, it's hard from the box plot because the pre-construction looks fairly symmetrical, but certainly during the construction is non-symmetrical. And again, when we do the during construction analysis, we conclude that it's not normally distributed. And that's not a problem. Non-normal distributions are real, and we have to deal with them. So that's a nutshell example of hypothesis testing applied to some real data. Let's summarize before we turn this over into the laboratory what we're actually trying to do. We're trying to ask the question, let's see if I can find a good picture. Well, I guess we're trying to ask the question, does the data support pregnancy or not pregnancy? And we looked at a series of tests. You're going to experiment with a few of these in the laboratory, and I'm going to stop right now and hand over the class to Farang and save my work.
If you want to have a short break, you can go on. We will begin the class in 3 minutes.
Where is my... Okay, now I don't have the Zoom thing interfering, but I have this cat in the way. Come on, move, guy. Just a bit. 25 pounds of furry love that is not going to move. Okay, lay down. If you're not going to move, just lay down right here. There you go. All right. There it is. Stop sharing.
When will the videos of lecture and lab for lab 14 be uploaded? I believe the answer is as soon as possible.
Yeah, the uploading is restricted by AT&T's unwillingness to provide their contracted service. So every hour that we spend live, just so you know, I'm just going to whine here. It takes about 3 hours to render the videos into an MP4 file, and it takes about the same amount of time to upload it. So every hour that we talk is a 6-hour activity. Fortunately, the computer does it, not me, but I do have to set up and put everything into process. Okay, Farang, you should be able to control the screen now.
Thank you. So while we're still in the break, I'm showing you the directory of the files that you need for Lab 15. There is one notebook, Lab 15 underline class, and then the same CSV files that we used for Tuesday. So if you have them, it's all right, you don't have to download them, but if for any case you do not have them, download them now.
Does it matter where they're downloaded? Because I have them in a separate file for 14. Do I need to download them again on my...
They're exactly the same file, so as long as you have them in your working directory, you're fine.
So it doesn't matter that's in my folder in Lab 14?
Are you using CoCalc?
Yes.
Then you should have this in the folder that you're running your Lab 15 notebook.
Okay.
So let me show you what I mean. So for example, my Lab 15 is being ran from this directory, and I need to have these two files in this list.
Oh, okay. Yeah, no, I have separate folders for every...
So then just paste the old files in the new folder, or download these and put it up there. It doesn't really make a difference.
All right, I'll go ahead and do that.
So, breaks time over. We are going to begin our lab. Open the chat box. Many of you seem to be too shy to talk, so you will probably feel more comfortable chatting. Okay. And then you have already seen my style. As I mentioned before, Dr. Cleveland is very, very gentle with you. I call names. So when I ask a question, just come out and answer. Otherwise, I'm going to call names. And unfortunate for those of you that I do know your names, they are going to come up more frequently.
How's that distributed?
Not very fairly. So, as I said, for Lab 15, you are going to need the Lab 15 underline class.ipynb file as your notebook, and then these two CSV files, which are identical to the ones that we use for our Tuesday session. Lab 14 underline E1 data and Lab 14 underline E2 data. I hope that by this moment you have all these, so we're gonna go and begin our Lab 15 session. On top of the notebook, you have your old familiar information cell that you're going to fill in with your information. we actually ended our last lab on a very important note. Do you remember where we stopped on Tuesday on lab 14?
No.
Oh, come on.
So the men in black, they did the flashy thing on you? They came and flashed you?
So I'm not sure how many of you are familiar with what's happening in this little GIF, but this is from the movie Men in Black, and that little device in Will Smith's hand would basically erase your memory or parts of your memory with that flash of light that you see.
Yeah, I don't even need that device. My memory self-erases.
So I have written this, that if you do remember where we were, I really am grateful. But apparently no one remembers, so...
Was it something to do with comparing like box plots and graphs to the distributions?
Yes, thank you, Ben. Thank you, my man. Yes, that was what I was looking for. We had a CSV file. The name of that file was lab 14 underline E1 data. In that data set, we had two sets of numbers. We did a bunch of the stuff. We used descriptive statistics, we used histograms, and we looked at it. Then we fit a normal distribution data model on it, and we decided that, okay, from visual assessment, we can say that normal distribution data model provides a good fit for both of our samples. And then we used normal distribution to generate two other samples based on the mean and the standard deviation of those samples. And then we compared them. We looked at them visually and saw them in terms of histograms and box plots. So in the first cell box, we are importing some of our external packages. And then these are basically the steps that we did on our lab 14. So we read the data set. We brought out set 1 and set 2 as NumPy arrays. We got the mean and standard deviation. We randomly, yes.
Was STD a standard deviation, right?
Yes.
Okay, cool.
Yes, yes. And then we used those parameters to generate another set of samples. We are calling that set 1S and set 2S. And then we basically went on and got plots in order to have visual comparisons. So this is a histogram showing my original set 1 in green, my original set 2 in red, my resampled set 1S in blue, and resampled set 2S in orange. And based on these, I asked you, I actually made a few assertions, and I asked you whether you think they are true or false. Since most of you have lost your memories, I have to do that again. So I'm going to make a few statements, and I want you to tell me whether you think they are true or false. Set 1 and set 2 are different.
True.
True.
True. Yes, indeed.
True. Yes, indeed.
True.
True.
Different distribution or just different in general?
Okay. At this point, my statement is set 1 and set 2 are different.
Okay, true.
True. True. Okay. My other assertion is set 1 and set 1S are similar.
True.
True.
True. True. True. Okay. My other statement is my set 2 and set 2S are similar.
True.
True, 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 true. And now that I'm on the mood of making assertions, I'm going to make another one, and I'm going to say my set 1 and set 2, my original two sets, are normally distributed.
True.
True, 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 true. Okay. Now I have a question. Come again?
I wasn't here for lab 14, so what is normally distributed?
So, a normal distribution, as explained during the lesson, is a distribution that looks like this.
So it's a bell curve distribution. Okay.
Exactly. Yes,
Okay.
that's another name for that. And the reason that they call it bell curve, because when you look at it, it looks like
a bell. Yeah.
a bell.
I got you.
So, when I was making these assertions, all of them, the 4 of them, I guess, how did you decide to accept or reject them?
By looking at the histograms created graphically.
Okay. We just looked at them. My eyes looked at them. Visuals. Okay, very good. That's where we were at the end of lab 14. We were using visuals, graphs, and looking at different plots to infer information about our population based on our samples. And we actually went on and also looked at box plots, and I again made those assertions, and in all cases you thought that I'm going to say the truth. So in the chat box prediction, we are going to use what we just did on these to find P. Good prediction. Yes. So based on what you learned during the lecture today about hypothesis testing, we are going to use statistical hypothesis tests to numerically and in a more formal and standard way decide whether these assertions that I made are actually accepted or rejected. In other words, we are going to have a look at our samples and decide whether we have enough evidence to reject the null hypothesis or my assertions or not. So let us go and see. On the first step, we are going to use statistical tests to confirm whether our sets are from normal distribution data model. What kind of test do I need for this purpose? Looking at looking at the list of tests that Dr. Cleveland showed you here.
Isn't it the Shapiro-Wilk test?
What kind of test is Shapiro-Wilk?
Oh, normality, yeah.
It's a normality test. So, on the same note, what is a normality test?
It's to see if it's normally distributed.
What's normally distributed?
The data.
Go on. Be more specific. Are you looking at the population or are you looking at the samples?
The samples?
The samples, yes. So, the whole idea behind the normality test is that you want to check and see whether your samples are from a normal distribution data model. What is the null hypothesis for a Shapiro-Wilk normality test?
That it is normally distributed?
That it is normally distributed. So, if I run the test and I find a very, very small p-value, what does that mean?
Reject null hypothesis.
Yes, and as Dooley and Brandon are all, Brandon, this is not about similarity anymore. So Dooley's answer is also correct. We are checking for normal distribution. So the null hypothesis, the H0, is that the samples are following a normal distribution. If I get a very, very, very small p-value, and we are going to talk about that, we are going to conclude that we have enough evidence to reject the null and say that the data do not follow a normal distribution. But if our p-value is not small enough, we are not going to be able to reject the null. Did you get that? So, my question is, when I say a very, very, very small p-value, what range of values am I talking about?
0 to 5%.
And what is that number?
0.00 to 0.00 or 0.05.
Yeah, how do you come up with 0.05?
It's the significance level, so if it's less than the significance level, then we can reject our null hypothesis.
Exactly. I'm quite proud of all of you. Should I go with 0.05 always?
No.
It's something more specific. Go smaller.
So if I go smaller, what happens?
You get a higher confidence level.
Exactly. So before we actually go and do this test, I have a question. If I tell you that you are going to pass this class with an A at a confidence level of 95%, would you feel good about what I've told you?
It's a weird question.
Yeah.
Yes.
Would you feel better if he said you'd get an A with a confidence interval of 50%?
In comparison between these two cases, in which one would you feel better? 95. 5%? Yeah. No, you don't want my confidence level to be 5%. Believe me.
That's putting a lot of pressure on yourself, Braden. 5%.
So the reason that I was asking that question, because I want you to very well understand the difference between confidence level and significance level. When we are talking about significance level, we are basically talking about how much error you are going to allow to exist in your final conclusion. So when you set your significance level at 0.05, or basically 5%, it means that you are 95% sure. That is your confidence level. They are complement. They are, what is the word?
They're one's complement of each other.
Yes, thank you. So 1 minus confidence level will give you the significance level. 1 minus significance level will give you the confidence level. Are we good? Do you have any questions on that?
I have a question actually.
Go.
So that significance level is a p-value, right?
No.
Damn
Very good question, actually. No, you're getting close, but do not get confused. The significance level is a cutoff, is like a landmark. It's a benchmark that you are comparing your p-value against. So you are saying that if my p-value is less than my significance level, I am going to reject the null hypothesis. They are not the same thing. You compare your p-value against your significance level.
Oh, so that p-value is my allowance for a mistake?
Your significance level is your allowance for a mistake.
you choose the significance level. That's a choice that we make. The p-value is computed. So
Exactly.
we make a choice of significance level. We compute a p-value. We make a decision based on the p-value's magnitude relative to our significance level that we chose ahead of time.
Okay, so then the p-value is given already.
No?
No, your p-value is going to be computed depending on what kind of test you're running, but it's going to be eventually based on your samples. You have nothing to do with your p-value.
But you have everything to do with the choice of significance.
Yeah.
And since we're having the discussion as a comparison, let's suppose that whatever we're deciding upon has to do with, I don't know, how quickly a train comes into a train station. That's not a supercritical thing. So we could choose a p-value kind of high. We maybe choose 20%. And if we're dealing with nuclear power plants and tsunamis, we might make our alpha value, our significance value, quite small because the consequences of failure are huge. And so we want to be absolutely sure that there are differences. And that's the choice we make as analysts. We do that ahead of time. Now, by convention, the common one that's used is 5%, and that's what we used in the lesson. And I think you'll see repeats of that in the laboratory. Another common one is 1%. But you as the analyst have a choice, and it's a decision you have to make ahead of time. You have to choose what level you're going to declare rejection at. Does that have you good and confused? I got him to stop talking, Farang. You can go on now.
So I saw a confusion in the chat box, and Dewey's answer is correct. We do reject the null hypothesis if the p-value is lower than the significance level.
That hurts, man. That hurts.
Why?
Okay.
So let me also give you another example. I think because that's the way I made peace with this whole content. Let's say that you're standing in a hallway. There is a giant red bottom on the wall. A guy comes in, pushes the red bottom, and gets $1 million in cash. Looking at this incident, would you go and push the red bottom?
Probably yes.
Probably yes. Yes, yeah. Okay. The second guy walks in, pushes the red bottom, gets turned into a pile of ash. Looking at both of these, would you go and push the red bottom?
Absolutely, yeah. I would personally do.
So, you're currently at a 50-50% situation, right? And you said that you would do it. So, the third guy walks in, pushes the bottom, gets turned into ash.
Yes.
I'll still do it. Yeah.
You're still gonna do that. Okay.
Yes, sir.
You stand there and you watch people coming in. After 100 people, you see 5 of them walk out with $1 million in cash, and 95 of them turn into ash.
Okay.
So there's a 5% chance that you walk out with a good amount of money, and 95% chance that you will die.
Okay.
Do you feel good about going on and pushing that red bottom?
No.
No. So what is happening here should give you an idea about the confidence level. If it was the other way, so if you stood on that hallway, 95 of those guys walked away with $1 million in cash, and 5 of them died, would you feel different about your decision?
Oh, yeah, sure.
Exactly. So, depending on how critical the decision is, we may feel different about where to put that significance level. So if I'm talking about a treatment for hair loss, and the worst thing that can happen is that nothing changes, the best thing that can happen is that the guy starts regrowth, then setting the significance level at 5% doesn't sound so bad. But if we are talking about a treatment that can either treat you or kill you, you probably don't want to go with 5% error allowance. You want your significance level to be lower, as low as possible.
Okay.
The thing is, it is impossible to go with 100% accuracy. So setting that threshold, that cutoff for error allowance is something that we get to do. We as the person who is doing the analysis, or in the engineer in this case. Sorry, Liana. But the p-value that you get comes directly from your samples and your observations. Do you have any questions about the ash or cash example?
I just wanted to ask, what do we call the p-value again? I'm sorry.
What is p-value? So going back to
Like the name of it.
The p-value here. The p-value, or calculated probability, is the probability of the collected data given the null hypothesis was true, or the probability of observing the collected data given the null hypothesis is true.
Okay.
The p-value, what the p-value tells you is whether you have enough evidence to reject your null hypothesis or not. Can you reject your underlying assumption or not? In the case of a normality test, it will tell you whether, based on your samples, you have enough evidence to say, no, this is not normally distributed, or you just can't reject it.
Okay, thank you.
Yeah. Do you have any other questions? Shall we move on?
Yeah, that kind of helped.
Come again, AJ?
So that
I
helps.
said yes, that kind of helped. You just continue.
Cool. So, for the normality test, we have different options. Here I'm going with the Shapiro-Wilk normality test. What we are doing is that first from the Skippy stats library, I'm importing the Shapiro function. And then very similar to what you saw in the lecture, I've basically done the CCMR. I have copied it. I'm citing Dr. Cleveland's lecture, and I have modified it for my data. I'm running this test for my set 1. So this is what I will feed to my Shapiro function. And then if I run it, oh, sorry. I'm going to wait for CoCal.
That's okay. I'm waiting for YouTube to upload the videos, so
Okay.
lots of waiting going
So-
on.
Running them all again. Okay. It's being super weird. Okay. Okay, now when I run my Shapiro function, Based on a cutoff that I'm setting to be 0.05, this is my significance level, I have defined it to be 0.05, it is going to tell me that, yes, the p-value that I got from my samples is 0.8, basically. So it is far away from 0.05. That means that the distributions that my samples are coming from is probably a normal distribution data model. It doesn't matter really, but I can go and change this 0.05 to 0.01 to raise my confidence level and make my significance level even lower. So the answer is not going to change because my p-value is so high. Do we have any questions about this cell and running normality test on my set 1? No? No? Okay. So, I'm doing the exact same thing for my set 2. The only thing that is changing is that I'm going with the set 2 column of my data set. This one is also from a Gaussian distribution or a normal distribution. What difference do you see here, though?
The p-value is smaller.
The p-value is smaller. What would you think about this difference? What does that tell you?
Does it mean that set 1 is more likely to be Gaussian? However you say that?
Yes, go on. Go on and rephrase your sentence. You're getting very close.
Like, the higher the p-value, the more probable it is to be a Gaussian distribution?
Yes. The higher the p-value, the more certain you are in not rejecting the null hypothesis. The story would be true the other way. So if your p-value is very, very, very small, like a tiny bit higher than 0, you can be rejecting the null hypothesis with more certainty. So that is one way of comparing p-values, but keep in mind that you need to make sure that you're comparing p-values for the same tests. Because the p-value is calculated based on the test statistic, and test statistic is specific to the test that you're running. You cannot go and compare the p-value of a normality test with a p-value of a non-parametric test and make inferences. That would be completely wrong. Kendall, can you unmute your mic?
Yes.
Okay. So here in this cell, I am running a normality test for set 2.
Okay.
The cutoff for my significance level is 0.05.
Right.
The p-value that I got is 0.15.
Right.
Is this higher than 0.05 or lower?
It's higher.
It's higher. So the fact that your p-value is higher than your cutoff means that
it's normally distributed?
Yes, it means that you cannot reject the null hypothesis, and since the null hypothesis was that it is normally distributed, you are going to say that it is probably normally distributed.
Okay, so like it doesn't matter like how much bigger it is than the p-value, right? Okay, just as long as it is bigger.
Yeah, the only difference that it makes is that if you compare this case and this case, you can say that set 1 has a higher probability of belonging to a normal distribution than set 2. That's it. But both of them, according to this test, they are normally distributed.
Yeah, that was kind of my question. Sorry, I forgot to put set 1, but I was wondering like between set 1 and set 2. So set 1 would be like more normally distributed.
I wouldn't say more normally distributed because it is not really a measurable adjective, but you can say that there's a higher probability that set 1 belongs to a normal distribution data model.
Okay, that makes sense.
Cool. So, Braden, yes, that is correct. Judging by the results of your Shapiro-Wilk normality test, you can say that both of these sets, set 1 and set 2, are probably normally distributed. And Travis, I think I've already answered that question. So if you have any other questions, let me. Then we went on and checked normality for our set 1s and set 2s. I have a question for you. Do you expect set 1s and set 2s to be normally distributed?
Yes.
Why?
Because they look somewhat symmetrical around their mean.
Okay, yes. That's
also
that I get.
P-value.
Yeah, but even without looking at it, the way that we define set 1s and set 2s is based on a normal distribution. So when we were defining them, we simply said that, okay, create a normal distribution with mu1 and SD1, and then generate 100 numbers out of it. So since they are artificially generated from a normal distribution, the test is not really meaningful at this point because, of course, they are going to be normal.
Is it possible the way that it's set up to run as like a normal, or to distribute itself normally? Could it be not normally distributed just with like a really low chance?
I would say if that happens, then there is something wrong with the function that we use to generate the samples.
All right.
Yeah. Audrey, the way that Braden has answered your question is correct. That really depends on how confident you need to be about your final conclusion. So, on the next step, we want to see, or we want to confirm, whether set 1 and set 1s are from the same distribution. What kind of test do I need? T. Anything else?
Yeah.
Liana, that is correct. Go ahead.
Pair t-test or whatever.
Pair t-test. Any other ideas?
The Mann-Whitney test, isn't that the one we used to compare on the lecture?
We actually used both of them. The Mann-Whitney U-test belongs to the family of non-parametric tests. And the t-tests and the pair t-tests are from the parametric statistical tests. Question: what is the difference between a parametric test and a non-parametric test? Like, what is the main difference? I like how all of you are going back to the lecture notebook and trying to find the answer.
That's good.
I think you will probably find it right before we start working on the examples.
Okay, that looks like a good answer.
Kalian, I'm not sure what you mean, but you're getting very close.
Yeah, that's not a bad answer, actually.
Mm-hmm. Yeah.
So what other things, Kayleen, what other things have parameters? Let's work on that answer, and we will lead everyone into the correct one. Functions have parameters, indeed. Any particular kind of functions we've examined recently, like in the last 2 lessons?
The normal distribution, like the population distribution.
Correct. For example, we looked at distribution functions. Aha. So
I want you all to come to, for example, the student's t-test explanation in your lecture notebook. If you notice on the list of assumptions, you have something like this, and then something like this. So the biggest difference between parametric tests and non-parametric tests is the assumptions. Parametric tests make certain assumptions about the underlying distributions of your samples. For example, a student's t-test needs your samples to follow a normally distributed, to follow the normal distribution. In an example like the one that we are dealing with, that's not going to be too much of an issue because, first of all, the numbers were not real, they were generated. And second of all, we have already checked and we know that they are probably normally distributed. In many real cases, that doesn't happen. So, for example, in the field of work that Dr. Cleveland and I are in, we deal with many data from natural resources, from stream flows, for example. And in many cases, in most cases, they do not follow a normal distribution. So using a parametric test is not always an option for us. Because in order to be able to rely on the results of a test, you need to follow the assumptions. You need to have them there. And for cases like that, non-parametric tests are very good. So we looked at the parametric and statistical hypothesis test, the student's t-test. Now I want you to scroll down and come here. So for example, for the Mann-Whitney U-test, if you look at the list of assumptions, you have this, which says that observations in each sample are independent and identically distributed. But if you notice, there is no assumptions about the underlying distribution. So it doesn't need you to have samples that are normally distributed. That is a great flexibility added to your analysis, especially when you are dealing with real data coming from the work. So if I want to go back, for the case of our lab, it doesn't really matter if you use the t-test or Mann-Whitney U-test because we already know our data is normally distributed. But I really want you to know the difference between the parametric family of tests and non-parametric family of tests. So for this, I am bringing in the Mann-Whitney U function from skippy.stats. I'm running that function on my two data sets, set 1 and set 1s. And then I'm setting up my significance level similarly to the ones on top at 0.05. And when you run this, it is going to report a p-value of 0.357, which is clearly greater than 0.05. And based on the results, I'm going to say that probably my set 1 and set 1s are coming from the same distribution. So notice the difference between the aim and outcome of a normality test and a test, a non-parametric test like Mann-Whitney U. Do you have any questions about the cell that we just covered? Kalian, you are right. We use non-parametric tests whenever we are not sure about the validity of the assumptions. For example, if you are not sure that our samples are from a normal distribution. But in this case, if you had used a t-test, that would be fine because we have already confirmed the normality. Braden, what do you mean? What do you mean by a double check? Yes. So as I mentioned, for the example that you're using in the lab, since the numbers are generated and we have already confirmed that they are from a normally distributed nature, we are good. But in many cases, we don't know that and we can't confirm that. So in those cases, going with a parametric test is not going to be an option. Any other questions?
Can I ask a maybe stupid question real quick?
There is no stupid questions. Go ahead.
So if you knew it was already normally distributed, you'd just use the Shapiro Wilk, and that compares it to it being normally distributed. But if you didn't know, you can compare it to a set that you know is normally distributed with Mann, Whitney.
Ben, if you notice, when I am running a Shapiro-Wilk test, I'm only feeding one set of samples. So I'm not comparing two sets or even more. It's only about one sample. You run the test on a set of numbers on one of your sample sets, and based on the p-value, you can judge whether that set of numbers follow a normal distribution data model.
All right, and the other one, you don't necessarily have to compare it to a normally distributed set. It's just a comparison between two sets.
In the second one, yes, you have nothing to do with the distribution anymore. In this one, I'm basically interested in knowing whether my set A and my set B belong to the same distribution or not.
All right, sorry to keep us here for so long.
No, don't worry about it. These are all good questions. So if you have questions, shoot. Parametric being the ones we did before the Mann, Whitney, right? Actually, if you look at the lectures notebook, it's always written on top. So one of the parametric tests that you worked on during the lecture was ANOVA, analysis of variance test. And then parametric and statistical hypothesis, paired the student's t-test, and another parametric was a student's t-test. In terms of non-parametrics, you worked on Mann, Whitney U-test, Wilcoxon signed rank test, and then Kruskal-Wallis H-test. I saw it somewhere here. Yes, if you're interested to learn more about different kind of tests, at least the more famous ones, definitely go and visit these links, especially the first one. These are excellent resources to learn and study more about these tests.
And they do a better job explaining than we can. So use those blog resources.
Travis, that is a very good question that is beyond the scope of this class. There's a thing about statistical tests that is called the power of a test. I'm not going to open that up, but you can actually go on Google and say, what is the advantage of parametric tests over non-parametric tests? And there will be very good resources that go into depth of this discussion if you are interested.
And power is related to that type 2 error.
Yes, the beta that you saw in that contingency table here. But I honestly believe that opening that can will turn this class into a statistics class,
and we're not
we don't
supposed
want
to
to
do that.
Yeah.
Exactly.
So, moving on, we went on and checked the same thing about set 2 and set 2 underline S, and the results with a p-value of 0.297 gave us the idea that set 2 and set 2 underline S probably belong to the same distribution. Liana, I know that sounds good to you. I know. But this is not really the time or the place. So, based on the results, we can say set 1 and set 1s probably belong to the same distribution. The same can be stated about set 2 and set 2s. Now let's check and see if set 1 and set 2 are significantly different or not. So, question. Based on what we discussed on the plot, do you remember set 1 and set 2 are different or not? We said true. I know you said true. What did that mean? Did that mean that they are the same or different? They're different. Diff. Okay. If I go on and run the Mann-Whitney test on set 1 and set 2, you will see that the p-value is extremely, extremely low. That means that you can go ahead and reject. No, I didn't lie to you. You can go ahead and reject the null hypothesis and say that set 1 and set 2 probably belong to different distributions. In other words, you can go and say that set 2 and set 1 are different. They are significantly different. Do you have any questions about it? So now, in addition to a visual assessment, you have run a statistical hypothesis test, and based on the results, on the basis of your samples, you are saying that probably they are different. And how confident are you? 95%. Very would be a good answer if we were having a daily conversation over 2 bottles of beer. But now that we are talking about statistics, you need to come down and talk about numerics. So 95% is a good answer. In fact, I can make you even more confident and run this again. And the answer is going to be the same. So you can be making that assertion with 99% confidence. Okay, moving on. The test results indicate that set 1 and set 2 belong to different distributions. And we can check the same for set 1s and set 2s. The same answer. And we can state a 95% confidence level that set 1 and set 2 are different. Do you have any question about any part of the example that we covered? Nothing coming through the headphone, nothing coming through the chat box. Okay. Now, for your exercise, since... What was the point of what, AJ? That is a very, very scary question. Of life?
I know, right? That's a very scary question.
So, what do you mean? Explain your question for me.
It's very hard to explain something that I don't understand.
You didn't understand anything that I said today?
I kind of like I understood the generals, but not the details.
Well, then probably you will need to rewatch the videos and go and check some of the resources that we left there for you. But just to give you an overall wrap-up, last session, we got to this plot. We have set 1, we have set 1s, we have set 2, and we have set 2s. And looking at the plot like this, at this box plot, we made a few assertions. We said, okay, it looks that set 1 and set 2 are different. It looks that set 1 and set 1s are similar, and set 2 and set 2s are similar. That's something that we made based on visual judgments. Today, we went and used the statistical hypothesis tests to confirm those assertions based on the p-value that was computed based on our samples and a given significance level that we define.
Okay.
So in the first case, in what we did on Tuesday, whatever we said was based on visual assessments. That is useful, but not solid enough in the world of science and engineering. Today, we learned how to back up an assertion that we can make based on visual assessment by using a statistical hypothesis tests. I hope that was helpful enough to some level. So about exercise 1, since most of you have lost your memories, I have to remind you again. In the previous lab, you worked on a data set that was from lab 14 _E2 data.csv. Again, it had 2 sets of data. You were asked to use the 2-key plotting position formula and fit a normal and log normal distribution data model, and then based on visual assessment, pick the one that fit your data better. And then once you found that better fit, you're going to use that model and create 2 sample sets, one for each set with 1,000 values. I think in lab 14, you were asked to create that with 100 values. For this one, go ahead and make it with 1,000 values. And then for this lab, you have 4 steps to take. On step 1, you're asked to define a data set with the original sets and the sample sets, with 4 columns, naturally, similar to what we did today. On step 2, you're going to use a normality test, and based on the result, decide whether each set belongs to a normal distribution data model or not. On step 3, you're going to use a parametric statistical hypothesis testing and confirm whether the sets are significantly different or not. You're going to make 3 comparisons in total. I hope that makes sense to you. And on step 4, you're going to use a non-parametric statistical hypothesis test and confirm whether the sets are significantly different or not. Again, 3 comparisons in total. So, do you have any questions about what you're supposed to do? Brandon, that is right. Braden, sorry. Braden, yes. Do you have any questions?
Or any confusion in the future? When are your office hours again?
Every Monday and Wednesday from 9 to 10 a.m.
All right, awesome. I appreciate it.
Yeah. Why 4 sets? You have 2 original sets, set A and set B, and you're going to generate 1 other set based on each one of them, so you will have set A, set B, set A resampled, set B resampled. Okay. Max, when you say define a data set, you mean put it into a data frame. Yes, that's true. Any other questions? Yeah.
I wasn't here on Tuesday, so I'll need to have an explanation of the Lab 14 real quick.
That
or
is
should I just watch the videos?
Yes, I would say that, because that's not something that I can do in the next 3 or 4 minutes. but you can definitely go and rewatch the videos. Make sure that you watch both lecture and lab. And then if you had any questions, come to my office hours either on Monday or on Wednesday.
Oh, sounds good.
One question I have in the chat box, Braden asks, could you explain why 3 comparisons? I have 4 sets. I'm comparing set A and set B, 1 comparison. Set A and set A resampled, 2nd comparison. Set A and set B resampled, 3 comparisons. 3 comparisons in total. Who was talking to me on the mic?
So our lab 14 and lab 15 are related to lab number 13?
They are not directly related, but you need to know what's happening in lab 13 in order to be able to understand what's happening in lab 14.
Okay, I think I understand the problem now, because I didn't understand lab 13 at all.
The word "at all" that you keep using, it keeps scaring me, man. When you do not understand something at all, there is not much I can do for you. But if you have a specific question, I can find answers for that.
Okay. Nice.
But then I know that you didn't come to my office hours on Mondays and Wednesday, but you can definitely join them if you have questions. So looking at the chat box, I went ahead and tried to make a data frame with set 1s and set 1, and it said that it can't do because they're different. Of course, delay. That's why I told you that you need to make 1,000 samples. Your set 1, make sure that your number of samples is equal to the number of original sets. Too many is a very relative combination of words. So in your lab 14 underline E2 data, how many numbers do you have under each column?
1,000.
Then you need to make 1,000 samples.
Boom. Nice.
There you go. Yes, that was probably the issue. In the E1 that we used in the class, we had 100 samples. In the E2 that is given to you, you have 1,000 samples. So just to clarify, we do a step 3 and 4 3 times. You can say that, but the 3 times that you do it will be considered a step 3, and then the other 3 times that you do for step 4 will be a step 4. They all have their own individual grades. Any other questions about exercise 1? Don't worry about it, Travis. Are we comparing 1 to 2, 3, and 4? No, you don't have to. You're comparing. If you follow what I did in the lab, you will get that. You're comparing set A and set B, the originals. Then you're comparing set A with its resampled and set B with its resampled. Just like what I did in the lab. Any other questions? So I know several of you wanted to meet me after today's lab. So if you want, you can go ahead and email me, and I will shortly send you a Zoom link for a private meeting. I see that the email has already begun. So Dr. Cleveland, I'm going to stop sharing my screen and pass the host back to you. Thank you all. Be safe and take care.
Thank you very much, Farhang. You're doing a great job, man.
Thank you. Appreciate it.
Pity they never say that about me, but okay.
Well, I mean, no, you too, obviously.
Thank you all for your attention, and the cat thanks you because he just rejoined us, and I had some comments to make that are relevant. So hypothesis testing is not as difficult as we seem to have made it. You're employing functions to either test an assertion about a single collection of data or about two collections of data to compare to one another. That's fundamentally all that's going on. And its value in engineering and other design aspects is not for things that are really far apart, like we used as examples where Farang had the set 1, set 1a, set 2, set 2a. You don't really need a hypothesis test for that. Its value comes when, if we were to plot them, they look really close to where we can't tell by seeing. And that's the whole point it's introduced. And they're used in medical research largely. They're used in sociological research. Ileana's going to use it to write insurance policies for us when she gets done. So this is a valuable activity. The difference between non-parametric and parametric is important because if we have evidence of parametric behavior, we can leverage that, and it gives us the ability to get that beta value in the type 2 error knocked down really small. If that's not the case and we use non-parametrics, those beta values are quite a bit higher, and there's other manipulations we have to do. So that's the whole point of the hypothesis test. I think you'll find with the examples, the scripts that we've provided will be more than adequate for you to complete the lab and deal with any exam questions that we're likely to ask on hypothesis tests. Just to scare the crap out of you, yes, there is an exam coming up. It will involve hypothesis tests. So good luck on that. I'll get this rendered and uploaded. I'll start the upload probably later today, so it's going to take it a while to get there. With that, have a wonderful day, everybody. Bye-bye. Be safe. Bye-bye.
You too. Bye-bye.
I hope have a good one.